Yeah, good morning, everyone. See, we are very few in number now, so I'm just allowing you to unmute yourselves. You can just talk to me when we are discussing. And even please inform your friends to join it. Okay, so let me just begin without wasting our time. Before starting the next case of finding particular integrals, let me just recall the previous two cases. If you remember, whenever you are given a particular differential equation, it looks like this: f of d into y is equals to q of x. Now, depending on this right hand side function, you are trying to find out what you call so depending on this right hand side function, you will find the solution. In fact, the solution includes two parts, right? One is the complementary function and other one is what you call the particular integral. When this right hand side function, you see in the case when we have discussed this, when this right hand side function q of x is an exponential function of this kind. Wait a second. Right. So when this right hand side function is an exponential function, you know how to find out the particular integral. So it is this idea. To find out the particular integral, we first of all, in fact, whatever may be the right hand side function, we write it like this: 1 by f of t, and you operate this on this right hand side function, exponential function, right hand side function in particular. And if it is exponential function, we directly substitute d is equals to a, right? And so that we get the particular integral as 1 by f of a into e to the power of ax. So this is your particular integral whenever f of a is not equals to 0. And in case if f of a is equals to 0, you see, we try to differentiate this denominator and simultaneously we multiply this with an x, right? So that was the thing we have discussed in the case of exponential functions. Similarly, as we discussed yesterday, when this right hand side function is either a trigonometric sine or cosine function, right? It may be either sine ax or sine bx, whatever you take, or a cosine function of this kind. Then we write the particular integral as this: 1 by f of t what you call 1 by f of d, for example, if it is sine ax. Now see, when it is sine ax, we just assume this as a function of d square, isn't it? So that we replace d square by minus a square, right? So by replacing it, so we may get a function of d again. We may get a function of d here. And then to get a function of d square again, we just try to take rationalization. After taking rationalization, definitely we'll get a function of d square, and we just repeat the above procedure. And in case when you substitute d square by minus a square, if you get a 0 in the denominator, Again, you see, as we discussed in the case of exponential functions, we try to differentiate this denominator and simultaneously we multiply this with our x. Okay, so that's the process we discussed regarding the previous two cases. Now, let's move on to the next case. When the right hand side function is function is an algebraic expression. Understand, I'm taking this as an algebraic expression, but it may be a polynomial also. I mean, if you have a differential equation of this kind, f of d, you may have some function on the left hand side, that doesn't matter. And if it is equals to, if you have it like this, x square minus x plus 1, right? See, everything here is an algebraic expression. In fact, if you add all of them, it becomes a polynomial, isn't it? So we are discussing this for a what you call algebraic expression, but that can be extended even for a polynomial on the right hand side. Not only polynomial, even if you have an exponential function as a sum to these three, instead of one, let us say if you have sine ax or sine 2x, then you know how to find out the particular integral. We just split it into 2 or 3 different terms depending on the number of terms you have. Now see, let's just understand what to do in this case. Now the question is clear. You have an algebraic function on the right hand side, and understand this power k is a positive constant. That is most important. See, what idea we have here is, for example, if you have this differential equation, let us say d square plus 4d plus 3 is equals to x to the power of 3. When you have an algebraic expression of this kind on the right side, we have an advantage of this kind. You see, if you differentiate x to the power of 3 once, what happens? You see, it becomes 3x square. And if you differentiate this again, I mean, if you differentiate x cube for the second time, it becomes, you see, 6x. Then if you can differentiate it for the third time, so it becomes a constant, 6. And if you differentiate it for more number of times, d power 4 x cube, then all other higher order derivatives become 0. See, because polynomial functions have this advantage, I just want to make use of this simple idea. Because algebraic functions vanish after successive differentiations, we try to use this idea while calculating the particular integrals of these algebraic functions on the right side. See what I'm trying to do here. When you are given this differential equation, you see it looks like this. F of d into y is equals to x to the power of k. Right? And then usual way, we write the particular integral. We write it as yp is equals to 1 by f of d, and you operate this on x to the power of k. Right? If you recall, for example, if you take this example, this into y is equal to x to the power of 3 you have, then what happens to the particular integral in a regular sense? We write it as 1 divided by d square plus 4d plus 3, and we operate all this on x to the power of 3. Right? See, the idea is, instead of having this d square plus 4d plus 3 in the denominator, if you have this in the numerator, for example, what happens? You see, we are going to operate this. I mean, you are going to operate d square plus 4d plus 3 on x to the power of 3. By chance, if it is there in the numerator. Okay. So when it is in the numerator, d square of x cube, you see, we have a simple thing. D of x cube, we have a simple thing, which you see. And when you multiply this constant with x cube, we can easily simplify, these things. So since we have certain advantage here, we just proceed like this while finding the particular integral. I'll try to take the lowest degree term common from this denominator. I'll try to bring these things, these derivatives to the numerator. So to get that, I'm trying to take the lowest degree term. You see here it is a constant. Lowest degree term common from this. So what happens? You see, 1 divided by, here is a 3. You're trying to bring it out so that you'll get it like this. 1 plus these things. D square plus 4d divided by 3. Isn't it? When I brought 3 out of this, you can rewrite it like this. And this still x cube remains as it is. What happens to see as a result of this? You can now take all this expression to the numerator so that you can write it as 1 plus d square plus 4d divided by 3 whole to the power of minus 1, x to the power of 3. Now you see, if you take all this expression d square plus 4d plus 3 as some x, if you just intuitively assume it as x, it looks like 1 plus x whole to the power of minus 1. Isn't it? We have a binomial series for this. If you recall, when it is 1 plus x whole to the power of minus 1, we can write it as 1 minus x plus x square minus x cube and so on. Don't you remember this? Now see, using this series expansion, we try to expand even this function which is in brackets. And thereby see what happens here. What is actually x here? It is nothing but d square plus 4d by 3. Right? If you take square of this, you will get d square plus 4d by 3 whole square. Then if you take cube of that, the same thing, power 3. But see, the idea what you have is, though you take more number of terms here, after fourth derivative, all other terms become 0. Since you have this advantage, even it has infinitely many number of terms here, that doesn't really affect our simplification. So what we are trying to do here, when it is this x to the power of k, see, I'm just taking it like this. This is our procedure now. Bring out the lowest degree term from f of d. See, f of d is in the denominator, so that when you bring lowest degree term out of this, then what happens to your particular integral? You see, yp is equals to, it becomes, you will get something like this, 1 plus or minus phi of d. Right? As a coefficient to this in the denominator, you may get something, but I'm not worried about that. Mostly that will be a constant. And this remains as it is on the right side. Now see, as we discussed, we are taking this to the numerator. So it becomes 1 plus or minus phi of t whole to the power of minus 1. And this x to the power of k remains as it is. And now, using binomial expansions, or else let us write the formula directly. Use these formulae. If it is 1 plus x whole to the power of minus 1, we can write it as 1 minus x plus x square minus x cube and so on. Or if it is, for example, 1 plus x, 1 minus x to the power of minus 1, then you can take all these terms with positive signs. Use these things to simplify what you call this particular integral. Right? So it's such a simple thing it is. See, when I explain you all these things, it looks very typical. But when I show you through an example, you understand it very easy. Right? The simplest thing, when it is an algebraic expression on the right side, you need to take the lowest degree term common from the denominator. That is the most important thing. When you take it, you will get a function of this kind, where the first term is, you see, always 1. See, the idea is to get a 1 here. To get a 1 here, you are bringing out lowest degree term. There is nothing else. Okay, so let's take a question. And meanwhile, you see, if you have any questions, if you want to communicate to me, you can use raise hand option. If you raise your hand, I'll just allow you to unmute yourselves. Now, see, let me take this question. Solve d square plus d plus 1 into y is equals to x to the power of 3. Right? Now look at this question. Clearly, the right hand side function is an exponential, what you call an algebraic expression. Wait a second. Some of the students are saying they cannot join it. Right. Now see, when it is this, as usually, when you are given an equation of this kind, the first part is we need to find what you call the complementary function. So to find out the complementary function, I'm just following the same ideas to find the complementary function. So to find the complementary function, we need to take what you call the auxiliary equation, isn't it? So the auxiliary equation for this question is m square plus m plus 1 is equals to 0. Right? Now see, you can find out the solutions of this equation using what you call the discriminant form. It is m is equals to, see, it's minus b, which is minus 1 plus or minus under root b square is, you see, 1 square, which is 1 minus 4ac. A is this 1, 4 times 1, 4 times, the constant c is also 1. So it becomes 4 divided by 2a is 2. Now, so this, if you can simplify, it is minus 1 plus or minus 1 minus 4 is, you see, root 3. So that we'll get it as root 3i by 2. And see, for my convenience, I'm writing it as m is equals to, I'm just trying to separate the real and imaginary parts, minus 1 by 2 plus or minus root 3 by 2 I. So clearly the roots are complex and even they are distinct, right? There are certainly no repetitions, and therefore the complementary function yc is equals to, it is c1 e to the power of minus 1 by 2 into x. So minus x by 2 multiplied by, look at it carefully, c1 cos, see the imaginary part what you have is root 3 by 2. So I'm writing it as cos root 3 by 2x plus c2 sine root 3 by 2x. So this is your complementary function. Now we need to find what you call the particular integral. So to find the particular integral. Now see, to find the particular integral, we just write it like this. Yp is equals to, see, the same thing I'm writing on the right side. Whatever the coefficient you have to y here, it is this 1 divided by d square plus d plus 1. And this you are operating on x cube. Right? See, whenever it is x cube, as I said, you need to take the lowest degree term common from this denominator. So in the denominator, in fact, the lowest degree term is 1 itself. Right? If it is some other constant, you need to bring that constant out of that. But since it is only 1, just I'm rewriting it for my convenience. Yeah. Subhaya, unmute yourselves.
Sir, in complementary function, y of c, why do we get c1, sir?
Oh, I'm sorry. This is not c1. It is only e power minus x by 2 and so on. You're right. Then, now see, I'm just rewriting it like this for convenience. It is equals to 1 divided by 1 plus, see, I'm writing the remaining 2 terms in a bracket. This is to say it is something similar to x, like it is 1 plus x now. And this you're operating on x cube. Now see, as we discussed, I'm just trying to take this to the numerator. So it is 1 plus d square plus d whole to the power of minus 1, and you're operating this on x cube. Right? It is this. Now it is similar to what you call 1 plus x whole to the power of minus 1, which you can write it as 1 minus x plus x square minus x cube and so on. And see, a question comes here. It's a series. So how many terms we should write? Look at the function you are given on the right side. See here, in this case, it is x cube, right? Write up to the degree whatever you are given here. Because it is x cube, right? While writing this series, write it up to x cube. When it is, for example, if you say x power 2 here, then it is enough if you take up to x square term. If it is x power 4, then you take up to x to the power of 4 term. Right? Following the function you are given on the right side, take up to the same term in this series. Now see, keeping that idea in view, I'm just writing this. This is equals to, now understand, this d square plus d is very much similar to x. So if you just expand this, you see 1 minus d square plus d, then plus d square plus d whole square, minus, because you see we have x cube, I'm taking it up to x cube term. Then minus d square plus d whole cube. Now all this is the expansion. I'm not taking the remaining terms, right? You can ask me why I'm ignoring the remaining terms. See, the idea is this: because it is x cube, if you differentiate it for the first time, we'll get 3x square. Then if you differentiate for the next time, it becomes a 6x. Then see, for the third time it is 6, and from fourth term onwards, I mean fourth time differentiation onwards, they all become zeros, isn't it? So here, if you take the next term, which is d square plus d whole to the power of 4, what is the minimum term you will get here? You see, when you expand this power 4, at least we'll get a term which involves d power 4, and all other terms in this expansion are higher powers to d only. There will be d power more than d power 4. So that if it, even if you operate them on x cube, certainly they'll become 0, you see. Right? Did you get my point? d square plus d power 4 ఉంది ఇక్కడ. దీన్ని మనం ఎక్స్పాండ్ చేస్తే ఇక్కడ వచ్చే మినిమం డిగ్రీ d power 4 టర్మ్. అంతకంటే మినిమం ఏం రాదు ఇంకా. మిగతా టర్మ్స్ అన్నిటికి కూడా డిగ్రీస్ దెర్ బి మోర్ దాన్ d power 4. దెర్ విల్ బి మోర్ దాన్ 4. సో వాటిని మనం ఎప్పుడైతే x power 3 మీద ఆపరేట్ చేస్తామో సర్టన్లీ యుల్ గెట్ దెమ్ యాజ్ జీరోస్. కాబట్టి వీఆర్ టేకింగ్ ఇట్ అప్ టు ఓన్లీ x cube term. Right? So we are simply ignoring the higher order terms in this series. That's a basic idea. So anyway, now let's just continue this. Let me expand all these terms. So this is equals to, first of all, I'm writing this one as it is and minus. Okay, let me write this d square plus d as it is. Then plus, now let me just expand this. It's like a plus b whole square, you see. A plus b whole square means it is d square power 2, you know. So it is d power 4 plus a square plus b square means d square plus 2ab, 2 times d square into d, which is 2 times d cube, minus, look at this carefully. Even if you expand this, for first problem, let us try to do this using this formula. A plus b whole cube, you know, which is a cube plus b cube plus 3a square b plus 3ab square. So if I use this idea, it is d square whole cube, you know, d power 6 plus b cube means d cube, then plus 3 a square b. A square means d square whole square, you know, d power 4 into d. It is d power 5 plus 3ab square. See, already d square is a, and if you take square of this d, it is also d square. D square into d square, it becomes d to the power of 4. So that you got all the 4 terms, you see, and you are operating all this on x cube. Right? See what happens because of this. I'll just write it in a simple kind of rough thing here. We have x cube, and if we differentiate it for the first time, as we discussed already, it is 3x square. We are going to use these things there now. If you differentiate it for the second time, it is 6x. Then for the third time, it is only a 6. And then for all other higher order derivatives, there will be zeros. Now see, let me operate each of these things one by one. First of all, I'm operating 1 on x cube. It is only x cube. Then minus, I'm just still writing these brackets, d square of x cube. See how much it is? 6x. So I'm writing 6x here. Plus, next you see d. d of x cube, differentiation of x cube, you know, it is 3x square. Then see, there is a plus sign. So I'm writing the plus sign as it is. And then see what you have. D power 4. See, the first term is d power 4. D power 4 of x cube, you see, it is 0 plus d square of x cube. See how much it is? 6x plus 2 times d cube of x cube. You know, it is 6. So 2 times it is 6. Then there is a minus sign, you see, minus. Look at it carefully. We have actually 4 terms in the next slide. You see from here, d power 6. For d power 4 itself, it is 0. So for all other higher order derivatives, d power 5, d power 6, d power 7, d power 100, they're all certainly zeros only. So when it is d power 6, it is 0. Let me write here. 0 plus, next term you see we have d cube. d cube of x power 6, it is I mean, x power 3, it is 6, then plus, see, then we have d power 5. D power 5 is also 0, you see, plus d power 4 is also 0. Right? So there you are. And all this is done. Just we have to stop this. Now it is equal to, if I simplify this, see how much you'll get. I'm just writing here all these things, 0 plus 6 plus 0 plus 0. Then if you can simplify this, it is equals to x cube. I'm just multiplying with a negative sign here, you see, minus 6x, then minus 3x square, and here you see plus 6x, then plus 12 minus, it is only a 6. So if you can simplify this, the particular integral yp is x cube, I'm writing the x square term, minus 3x square, then minus 6x, and here also here it is plus 6x. See, you can cancel them, right? So there are no more x terms, plus 12 minus 6, it is 6. That's your particular integral. Now if you can write the final what you call the solution, the general solution is y is equals to yc plus yp. That is, y is equals to, see how much you got the complementary function. It is e to the power of minus x by 2 times c1 cos root 3 by 2x plus c2 sin root 3 by 2x, and all this plus, this particular integral, whatever you got here, x cube minus 3x square plus 6. So that's your particular integral. I mean, that's your solution. So in simple, you see what you have done. You have simply calculated the complementary function first, and whenever it is an algebraic function on the right side, you have simply taken out this lowest degree term, and then by using this binomial expansion, you have just expanded everything, and then you have operated each of these terms on x cube. Right? Using these ideas here, you have simply operated everything on x cube, and after simplification, you got directly what you call the required particular integral. And then usually, as we know, sum of complementary function and particular integral is the general solution. Right? If anybody have any questions, please use your raise hand option so that I can clear your questions. Right. Now let's take the next question. Now see, if you take this question, let me take a cubic equation now. It is d cube minus 3d plus, 3d minus 2. And if you operate this on y, it is equals to x square. Right. See, it is now. See, usually the same problem. We need to find out, first of all, find out what you call this complementary function. So to find out the complementary function, as we know, we take it like this. You see, auxiliary equation m cube minus 3m minus 2 is equals to 0. Right? See, to find out what you call the solutions of this auxiliary equation, you must be a little careful. Some of them may be complex, some of them may be real. So I'm just using my calculator to calculate the roots of this equation, you see, with this. So this is a calculator you have with you. So I'm using my calculator. So it is, I'm using this, you see, mode. The calculator is in fifth option. I mean, the equation is in fifth option. So I've selected, I have a cubic equation here. So it is the fourth one. And the equation what I have is m cube minus 3m minus 2. So the coefficient of m cube is 1. Then see, I'm clicking on is equal to button. Then see, there is no m square term in the given equation. I mean, the auxiliary equation. So I'm taking the coefficient of m square as 0 is equals to, then the coefficient of m is minus 3. So it is minus 3 is equals to, and the constant what you are given is minus 2. So as a result of this, you can see here, x1 is 2, which means the first root is 2. And see, x2 is minus 1, it is showing. Correct? Then look at it carefully. It is not showing you the third root. When it is not showing you the third root, it means that second root is repeated. Right? Don't take directly this one as the third root. Look at it carefully. x1 is 2. In your calculators, x1 is 2. Then x2, it is showing you as minus 1. If there is a third root, it must show you as x3 is equal to so and so. But you see what happening when I click on this is equal to button, it is directly moving into that input values. It means that second root, whatever was displayed earlier, that is repeated for the second time. Okay. So keeping that idea in mind, now the roots are 2 comma minus 1. Okay. So let's come back to this. Now see, if you solve this by using calculator, we can in fact write it as m is equals to 2 and m is equals to minus 1 comma minus 1. Right? If you don't have a calculator, what can you do? You can directly randomly substitute and check your answers, or else you can use that synthetic division method, whatever you feel convenient. So these are the roots, and minus 1 is a repeated root here. Now, keeping these things in view, if you can write the complementary function, yc is equals to, see, corresponding to 2, we can, because they are all real roots, corresponding to 2, we can write it as c1 e to the power of 2x plus, corresponding to this repeated root minus 1, we can write it as c2 plus c3x into e to the power of minus x. So that's your complementary function done. Now let's calculate what you call the particular integral. Now see if you can calculate the particular integral. We need to take it this way. Yp is equals to, look at it carefully, 1 divided by d cube minus 3d minus 2, and you're operating all this on x square. Now see, when it is an algebraic expression, as we discussed, you need to take the lowest degree term common. Which is the lowest degree term here? You see, don't say it is only minus 2. I mean, don't say it is only 2, but we need to take the minus 2 common from this. See, what is our idea? After taking this, common from all these terms, you must get a term of this kind, 1 plus x or 1 minus x kind of things. You are simply expecting a 1 there. To get a 1, you are taking certain things common from this. So if you want to get a 1, you must take minus 2 out of this. So I'm just taking minus 2 common from these three terms. So that if I take a minus 2 common from this, first of all, I'll get a 1, then minus d cube minus 3d divided by 2. See, for d cube and minus d, I've just kept, the same constants, but because I've taken minus 2 common from that, you see, I've divided it by minus 2. Right? So here it is, and this you're operating on x square. Now for convenience, if you can write it again, it is minus 1 by 2. You can just keep this aside. And if you can take this to the numerator, it is 1 minus, see, I'm just writing it in brackets, 3d d cube minus 3d divided by 2, hold this to the power of minus 1, and you're operating this on x square. Right, so here you are. Now it is very much similar to what you call 1 minus x whole to the power of minus 1. So if you recall that 1 minus x whole to the power of minus 1, the formula says it this, 1 plus x square and so on. See, I'm interestingly observing this x square. Because it is x square here, I'm just taking it up to only x square term, right? As we discussed already. Now, therefore, our particular integral is yp is equal to, here is a minus 1 by 2. I'm writing that as it is, then it's like 1 minus x whole to the power of minus 1. Means x here is this function which is in brackets, d cube minus 3d by 2. So I'm just substituting everything here. It is 1, first of all, plus d cube minus 3d by 2. Then plus, I'm taking the square of this, d cube minus 3d by 2 whole square, and so on, right? So other things are not necessary to write. So you can just stop here and you can operate these things on x square. So this is equals to, see here I'm writing it for convenience. We have the function x square, right? So if you differentiate it for the first time, differentiation of x square is 2x. And if you differentiate it for the second time, it is 2. And if you differentiate it for, higher terms, when it is third time or fourth time, even all higher order derivatives, they all become simply zeros. So I'm just going to use these things while simplification. So this is equals to minus 1 by 2 into, now, do you want me to expand this or shall I write it directly? I just want to mention one point. If you look at the previous question, look at this. We have d square plus d whole cube. We have expanded this. In this expansion, you see the lowest degree term you get here is d cube. All other terms are of, the higher degree than 3. So that all other terms become certainly 0 except this d cube term. Isn't it? Because it is power 3, you are taking cube of this. The lowest degree term you may get here is d cube term. All others will be more than that. Certainly their derivatives, when you operate them on x cube, you will get them as zeros only. The same thing happens even in this question. See here we have d cube minus 3d something by 2 whole square, and you are operating all this on x square. So when you take square of this, the lowest degree term you may get is a d square term. And all other terms you will get they are more than this d square term only. So when you operate those terms on x square, certainly they'll become 0, that is a clear understanding. Certainly as they become 0, why should we consider them again? Why should we waste our time? Right? So keeping that idea in view, we just proceed like this, you see. First of all, I'm operating 1 on x square. So it is x square. Then here it is a 1 by 2, I'm just writing that 1 by 2 aside. Then in brackets, if you operate d cube on x square, see how much it is? 0. Minus here is a 3. Then you're operating d on x square. It is 2x. 3 times 2x. So I'm just closing this. Plus, see what you have here. 1 by 2 whole square is there. So I'm writing a 1 by 4 aside. And see, as we discussed now, when you take square of this, the lowest degree term what you get here is minus 3d whole square, which is 9d square, 9d square is the lowest degree term you get here in expansion of this square. All others are more than this d square. So they are absolutely not required to write because you're operating them on x square. See, by chance, if it is x cube here, then certainly you must expand them, right? Only in the last term of whatever we considered, in the last term, you may ignore the remaining, or you can consider only the lowest degree term, right? The other terms can be ignored. So, or otherwise, if you don't want to have all this confusion, you can even expand that. It's up to you. So the lowest degree term, what you get here is 9d square. So if you operate that 9d square, 9 into d square of x square, you see, as I have written it already, it is 2. 9 times 2. The remaining terms in this expansion become 0 when you operate them on x square. Now see, this is equals to minus 1 by 2 into, it is x square. Then see here it is. This 2x by 2 is there, this 2 can be cancelled here. So the remaining is only minus 3x plus here it is 2 times 2, we get it as 9 by 2. So this is your particular integral. Right now, therefore, the general solution is y is equals to yc plus yp. So that is y is equals to, see the function, complementary function, what you got, c1 e power 2x plus c2 plus c3x into e to the power of minus 2x minus x, or this is your complementary function, plus particular integral is this, you see there is a minus, so I've written minus 1 by 2 into x square minus 3x plus 9 by 2. right? So like this, you can write the particular integral or the general solution of this particular function. So if you are all fine, let's take one more question, which include even the previous cases. If you have any questions, you can ask me now. You can raise your hand, so I'll allow you to unmute yourselves. Okay, then fine. Let's move on to the next. See, by this question, you must understand everything carefully, because this is somewhat important one. Solve d cube plus 2d square plus d. Look at it, there is no constant. And this multiplied by y is equals to, we have an interesting right hand side function here, e power 2x plus x square plus x plus sine 2x. Right, see, that's your right hand side function. Now this is equals to, see how to find out solution for this differential equation. Right, so when there is no constant, we must have some other interesting things, and in fact there are some interesting functions even on the right side. Let's do this carefully. Now first of all, to find the complementary function, so you see, to find the complementary function, we need to take what you call the auxiliary equation first, and it is m cube plus 2m square plus m is equals to 0. So to find out the roots of this equation, you can take m common from this. So it is m times m square plus 2m plus 1 is equals to 0. And hence you can understand the roots are, in fact, you can write this m square plus 2m plus 1 as m plus 1 whole square, So it is m plus 1 into m plus 1 is equals to 0. So you can clearly understand the roots are m is equals to 0, m is equals to minus 1, and m is equals to minus 1. Right, so clearly they are the roots. So now corresponding to these roots, if you write the complementary function, it is yc is equals to, now see, corresponding to 0, it is c1 e to the power of 0x. Right, e power 0x is anyway what you call 1, so you can even ignore that. I mean, you will write only c1 here, plus corresponding to this repeated root minus 1, we can write it like this. You see, c2 plus c3x e to the power of minus x. So that's your complementary function. Now we need to calculate what you call this particular integral. To find this particular integral, see, interestingly, I'm writing it like this. Yp is equals to, it is this 1 divided by d cube plus 2d square plus d, and this you're operating on e power 2x plus x square plus x plus sine 2x. Look at this function carefully. You can expect questions of this kind in the examination, because you see on the right hand side, we have all the three combinations. We have a exponential function, we have a polynomial, and we have what you call a trigonometric function. When everything is there, you see, this kind of questions can be given even for 10 marks sometimes. Okay, so concentrate on questions of this kind. And now see, what can we do here? Whenever you have a what you call combination of functions like this, we try to split it into two or three different particular integrals, 2 or 3 different parts. So I'm just doing the same thing here also. First of all, it is 1 divided by d cube plus 2d square plus d. I'm taking now this operating on e power 2x plus 1 divided by d cube plus 2d square plus d. This you're operating on. See, we have no need to take these two separately. Both are what you call polynomials, both are algebraic functions, Let's take them together. So this has one simple function, x square plus x. And then if you take the other one separately, which is 1 divided by d cube plus 2d square plus d, which you are operating on sine 2x. right? Now let's take these three one after the other individually. Now, first of all, I'm considering the first one. See, 1 by dq plus 2d square plus d operating on e power 2x. See what happens to this. It is equals to, recall what we do. When it is an exponential function, what we do? When it is an exponential function, directly we substitute d is equals to this coefficient of x in the power. So it is 2 here, right? Now directly let us substitute d is equals to 2. And if you get a 0, there will be a problem. Otherwise, no issues. So if I do this, 1 divided by 2 cube is 8, plus 2 square is 4 times 2, it is also 8, plus d, it is 2. And this e power 2x remains as it is. That implies, see what you'll get here. 1 by 18, you're getting a non-zero value. So this itself is the particular integral corresponding to the first part of this. Okay, you got it, fine. Let's keep that aside. Now let me take the second one. Consider 1 divided by, what you have here, you see, dq plus 2d square plus d, and you're operating this on this polynomial x square plus x. But it looks fine. Now see, this is case 3, where it is algebraic functions. You need to take the lowest degree term common from the denominator. Earlier in the previous two problems, when the constant was the lowest degree term, we brought it out, isn't it? But now there is no constant. So which is the lowest degree term here? It is d. Whatever the lowest degree term you have there, we need to bring it out. That's the idea. So since the lowest degree term here is d, you need to bring d out of this, right? So let's do that. So you can write it as, it is equals to 1 divided by, see, I'm writing d aside in the denominator. So d multiplied by, what remains there? You see, when you take d out of this, first you will get as 1 plus, when you get d out of this, you will get a d square plus 2d, isn't it? So when you take t common from these remaining two terms, you'll get these two, and you're operating now this on x square plus x. Now see, let me write this 1 by d as it is. I operate this 1 by d at the end after completion of the remaining portion. And if you take the remaining part to the numerator, you will get it like this: 1 plus d square plus 2d whole to the power of minus 1, and you're operating this on x square plus x. Right? Now see, if I just expand this, let me write this 1 by d as it is. And if you just expand it, it's like 1 plus x whole to the power of minus 1. If you expand that, what happens? You see 1 minus x, which is d square plus 2d, then plus one point here, up to what term we should consider this? It's a series expansion. So up to which degree term you need to take this? Look at this polynomial. We have the highest degree in this as x square. 2 it is, correct? So since the highest degree is second one here, you need to take up to second degree term even in this expansion. So take up to square term, d square plus 2d whole square. And the other terms can be ignored because there are no other powers of this. So this you are going to operate on x square plus x, right? I'm just trying to take this here. You see, we have actually x square plus x. When you differentiate this for the first time, if you differentiate this for the first time, differentiation of x square plus x is 2x plus 1, isn't it? If you differentiate it for the second time, d square is, differentiation of 2x is 2, plus for 1 the derivative is anyway 0. If you can differentiate it for the third time, you see it is 0. This is how just simple it is. So let me use these things while simplifying all these things here. Let us take this 1 by d as it is. Then if you take 1 on x square plus x, it is x square plus x itself minus, look at it, d square of x square plus x. See how much it is? D square is, okay, let's do it once without directly writing it. Let me simplify this. There will be a problem because there is an x also. D square plus 2d plus, if you take square of this, it is d power 4 plus 4d square plus 2 times 2d into d square, it is 4d cube. And this, if I operate on x square plus x. See, now let's write it. 1 by d into 1 operating on this, it is x square plus x minus d square of x square plus x. See how much you got it. 2. I'm substituting that 2 here. Plus 2 times d of x square plus x. You see, it is 2x plus 1. Plus, now this is interesting. D power 4. See, d cube itself is 0. So automatically d power 4 is also 0. Fine. Plus 4 into d square. See how much is d square? It is 2 plus 4 times d cube is also 0. So let me just take this as 0. Here you are. Now let me just simplify this in the next slide. So it is equals to, we have a 1 by d there. And see what remains there. First of all, you have x square plus x. So I'm writing that x square plus x as it is. Minus, look at this carefully. I'm just splitting this into 2 different terms. 2 plus 2x plus 2. Look at it carefully. We have minus of 2 plus 2 into 2x plus 1. So we have a 4x here. 4x plus 2. Then see the last term. It is only a8. The remaining 2 are zeros. So it is just a8 plus a8. Now see if I can simplify this again. It is 1 by d into x square plus x. Then see it is minus 4x. Then 2 plus 2, it is 4, you know. So it is minus 4 plus 8. Now if I can simplify this again, it is 1 by d into x square. See, it is x minus 4x. So it is minus 3x. Then 8 minus 4, it is plus 4. Now see, here you are. So you have operated all this, you know, except 1 by d, whatever the remaining you have operated all these things on x square plus x. As a result of that, you got it as x square minus 3x plus 4. Now it's a time to operate 1 by d on this expression, right? We know already d refers to differentiation, isn't it? And when it is 1 by d, it is integration. So keeping that idea in mind, if you can integrate this, integration of x square is x cube by 3 minus 3 times integration of x, it is x square by 2 plus integration of 4, as we know, it is 4x. So therefore, if you just write all this, 1 divided by d cube minus what is our question, you see, d cube plus 2d square plus d. If you operate this on y, not y exactly, this x square plus x particularly. So we got it as x cube by 3 minus 3x square by 2 plus 4x. Right. So this is the second part of your particular integral. Right. So we have 3 parts in our particular integral. First one we got directly as 1 by 18 into e power 2x. And the second one, now you got it as this. Now we have one more part, you see. We need to operate this on sine 2x. Right. So here it is interesting. Now let me take the third part. Consider 1 divided by d cube plus 2d plus d. We need to operate this on sine 2x. Right. So if you can recall this, when it is a trigonometric function, we will always simply write d square is equal to minus b square, isn't it? So now we need to replace d square. Wherever you have d square, you need to replace it by minus b square. B means 2 here, you know, it is minus 4. So instead of d square, we should write it as minus 4. That's the idea. So therefore, it is equals to 1 divided by, look at it carefully. Yesterday, we had not discussed problems of this kind. We have a d cube here. As we know, we can write d cube as d square into d. Right? So that instead of d square, you can substitute this minus 4. We cannot leave that. Right? Wherever you have d square, you should substitute it by, you can replace it by minus 4. So though it is a d cube, you should write it as, first of all, d square into d, and in place of d square, you must substitute this. So therefore, you will get it like this. If it is d cube, we'll get it as minus 4 into d. In fact, it is d square into d. So in place of d square, you have written a minus 4 plus, there is no d square. Something went wrong. It is d square only. Correct? Yeah, it is 2d square. Now, so here it is 2 times in place of d square. Again, I'm writing minus 4 plus. Now there is a d. So instead of d, you're not substituting anything. So I'm writing the d as it is. And of course, this sine 2x also. Right? Now, if I simplify this, see what will you get? It is equals to then 1 divided by, here it is, look at this carefully, minus 4d plus d. So it is minus 3d. Then 2 times minus 4, it is minus 8. And this you are operating on sine 2x. Right? See, as we discussed yesterday, again, we got a function of only d. But to get a function of d square, we need to take rationalization. So I'm just multiplying and dividing this by 3d minus 8. Right? So 3d minus 8 divided by, see, here we have, see, if you have a confusion in this, try to take a minus common from those two so that you will get a clarity. So here we have a minus 3d minus 8, and I'm multiplying this with what you call 3d minus 8 in the denominator. So it is sine 2x. Right? So now this 3d minus 8 in the numerator remains as it is, but in the denominator it is like, minus a plus 3d minus a minus 3d, a plus b into a minus b. So if we take a square minus b square, it is a square minus b square, it is minus 8 whole square, it is 64 minus 3d whole square, 9d square. Yes or no? So this into sine 2x. See, if you have this confusion, you can take a minus common from the denominator so that it looks like this. If you take a minus common from this, it is minus of 3d plus 8. So when it is 3d plus 8, you are simply multiplying and dividing it by 3d minus 8. So when you do this, what happens? You see, minus of 9d square minus 64. If you multiply these two, 3d plus 8 and 3d minus 8, it is 9d square minus 64. But when you multiply it with a negative sign, you will get this 64 minus 9d square. In either ways, you can do that. Now see here again, you are substituting d square is equals to minus 4. So this is going to be 3d minus 8 divided by 64 minus 9 times minus 4. So this operating on sine 2x. So it is equals to, I'm just writing here itself, 3d minus 8 divided by minus 4 minus 9, it is 36. 64 plus 36 is 100. And this you're operating on sine 2x. So this is equals to, if you can write this 1 by 100 aside, you need to operate 3d minus 8 on sine 2x. So which is equals to 1 by 100 into, see if you can differentiate this. There is a 3 already. If you differentiate sine 2x, it is first of all cos 2x. And if you differentiate 2x, it is 2 minus 8 times sine 2x. So which is equals to, you see, we'll get the particular integral for this as 1 by 100 times 3 times 2, it is 6 times cos 2x minus 8 times sine 2x. So we got the particular integrals in the 3 different parts of this. So therefore, if you finally write the particular integral yp is equals to, you need to add these 3. See, the first one you got as this 1 by 18 into e power 2x. I'm writing that here. 1 by 18 into e power 2x plus the second one, you see, we got it here. It is x cubed by 3 minus 3x squared by 2 plus 4x. And finally, you see, we got this 1 by 100 into 6 cos 2x minus 8 sine 2x. So therefore, the general solution, finally, we add what you call the complementary function and particular integral yc plus yp. So that is y is equals to, if you look back, what is the complementary function? It is this. C1 e power 0 is anyway 1, so I'm not writing. So it is simply C1 plus C2 plus C3x into e to the power of minus x. This is all your complementary function plus particular integral. You see, I'm writing all this as it is. So it is 1 by 18 e to the power of 2x plus x cubed by 3 minus 3x squared by 2 plus 4x plus 1 by 100 into all these things. You see, 6 cos 2x minus 8 sin 2x. So that's your final solution. And see if anybody have any questions in that, you can. So this is one important and interesting question on this. So if everything is okay here, let's move on to what you call the next case. In fact, you see, if you are thorough in these three cases, you can understand the remaining cases very easily, because the next case is a combination of the previous three cases. Now see, I'm taking the next case. Now see, here it is. If the right hand side function q is, see, in the previous three cases, we have considered a single expression. We had seen it may be an exponential function. It may be a trigonometric sine or cos function, or simply it may be an algebraic expression of this kind. Right? Nowhere it is a product of two functions. We may have sometimes combination of functions. I mean, sum of 2 or 3 different functions, but we had not seen product of 2 different functions. Now case 4 is of that kind. When the right hand side function q is this e power ax into v. Right? V is again a function of x, and in particular, what possibilities we have for v? Understand it this way. Where v is a function of x, in general, v may be any function of x. But in particular, we take only few possibilities to x. Like you see, as we have considered only these two functions, I mean, these three functions, basically, exponential function, trigonometric function, and algebraic expression. So as we have considered only these three in our syllabus, the chances for v are the remaining two. As you have already exponential function here, to be a function v here, you can take either a trigonometric sine or cos or any algebraic polynomial. So you may have a problem of this kind. F of d into y is equal to e power x into x square. Or else you may have a function like this on the right side, e power x into sine 3x. Right? Something like e power minus x into cos 3x. So these things are allowed, but you cannot take any other random functions. Even if you take them, there are other techniques, but we are not discussing them in our syllabus. Okay, so let's just begin what to do when the right hand side function is this. Now, so here you are. So this is your differential equation. Left f of d into y is equals to e to the power of ax into v is your right hand side function. Now, therefore, because of this, we write the particular integral as in this, you see. Particular integral yp is equals to 1 by the regular way, 1 by f of d operating on e to the power of ax multiplied by v. Right? As I said, this v can be either an algebraic expression or a trigonometric function. Right? We cannot take the other things because we don't have the other methods. I mean, we have not discussed the techniques when the functions are other than those two. Now see here, when you have this kind of expression for the particular integral, understand this carefully. To write the particular integral now, we need to take out this exponential function e power ax to the left side of this f of d, 1 by f of d. Means, write this e power ax on the left side to 1 by f of d and replace every d by d plus a. So that we write it like this, 1 divided by f of d plus a. So that because of this, you see, you will get a new function of d here, and you operate this on this capital V. Right? So what you have done here, take out e power ax to the left of 1 by f of d and replace every d by d plus a. This is how what you can say, f of d becomes f of d plus a. Right? Now, after getting this, we need to operate this 1 by f of d plus a on V. See, for example, just to understand it this way, what happens? I'll just take a simple example and tell you this. See, for example, if you have this differential equation, dq plus 4d minus 2 into, let me take square term, into y is equal to, let us say, some e power x into x square. Right? Because of this, what happens, you see, while writing the particular integral, yp becomes this, 1 divided by d square plus 4d minus 2, and you operate this on e power x into x square. So as I said, when it is a product of two functions of this kind, see, we have a clear product of two functions, e power x into x square. When it is this, we need to write this e power x on the left side. Right? See, the idea here is, when you write it on the left side to 1 by f of d, when you write it on left side to 1 by f of d, you are not going to use this exponential function in further simplification. You just keep it aside. You never use that anymore. That's a basic idea. So when you write e power x on the left side to this, you need to replace d by d plus a, means d plus 1 here. See, the coefficient of x is 1, right? So wherever you have a d, in place of d now, we need to write it as d plus 1. So it becomes like this, d plus 1 whole square plus 4 times d plus 1 minus 2, and you just write only this remaining function x square here. See, instead of x square, if it is sine 2x, you just continue that sine 2x here. Okay, then it is equal to e power x. See, this e power x remains as it is till the end of problem. Finally, we just write that e power x as part of the solution, but we never use that. Now see if you can simplify this. What happens, you see? 1 divided by, if you just expand this, it is d square plus 2d plus 1 plus here also it is 4d plus 4 minus here is a 2. And this remains as x square. So this is equal to, it is e power x into 1 divided by, if you simplify this, it is d square plus, 2d plus 4d, it is 6d. Then what remains, you see, 1 plus 4, 5, 5 minus 2, it is 3. And this remains as x square. Now see, if we just ignore this e power x, don't we know how to solve this part? Don't we know how to evaluate that particular integral? Because it is x square here, we need to take out this lowest degree term. So by taking a 3 common from that, we use the idea of 1 plus x whole to the power of minus 1, and we simplify that. So this is in the case of algebraic functions. By chance, instead of in place of this, if you have it like e power x into sine 2x, it may be anything, in fact, sine 2x or sine 3x, anything is okay. In place of that, if you have this, again, here also you send e power x to the left side, but in place of this x square, you keep it as sine 2x. And after simplification also, you still write this as sine 2x only. But when it is sine 2x, what we do? We just replace it d square by minus 4. Right? What happens, you see, when it is a function of this kind on the right side, when the right hand side is a product of two functions, we are simply reducing the problem into one of the earlier cases. Right? By sending e power ax to the left side of this 1 by f of t, you are reducing the problem into one of the previous cases, right? It may be either a case of algebraic expression or a case of trigonometric function, right? By reducing it into the previous cases, we simplify the problem, right? There is nothing else. So when you are good enough in the previous cases, you can understand this very, very easily. The only additional thing what you have here is sending e power ax to the left side and replacing d by d plus a. Except that the remaining things are almost as we discussed in the previous cases. So let's take a problem on this and understand this. Question 1 on this. Solve d square y by dx square minus 7 times dy by dx plus 6y is equals to e power 2x into 1 plus x. Right? So if it is this, let's see how to find out the solution. Now see, we can write the differential equation as in this, because they are given in derivatives form. Let us write it in operators form. When it is d square by dx square, we can write it as d square minus this is 7d plus this is 6. And when you operate all this on y, on the right hand side, we have it this e power 2x into 1 plus x. Right? Now see, as usually, we need to first of all find out what you call the complementary function. So to find out the complementary function, you need to take what you call the auxiliary equation. So it is auxiliary equation is m square minus 7m plus 6 is equals to 0. So we can write this as m minus 1 into m minus 6 is equals to 0. So from here you can write m is equals to 1 or m is equals to 6. So we have clearly two real and distinct roots, right? So therefore, we can write the complementary function yc as c1 e power x plus c2 e to the power of 6x. Right? So that's a complementary function. Now let's find out what you call the particular integral. To find the particular integral, and see, it is yp is equals to 1 divided by d square minus 7d plus 6, and this you're operating on e power 2x multiplied by 1 plus x. Understand, this 1 plus x is an algebraic, what you call a polynomial, right? 1 plus x is a polynomial, and hence it is just like e power ax into v. I mean, v is this 1 plus x, right? Because you know how to simplify this when it is 1. 1 can be written as e power 0x, you know. So keeping that in mind, I'm taking v as 1 plus x. Okay, let's do this. And it is equals to, when you have a product of two functions like this, you have a product of two functions and in which one is an exponential function. So we need to send this e power 2x to the left side of 1 by f of d. So we just write it on the left side, e power 2x, and now we replace d by d plus 2. See, the coefficient of x is 2, right? So we are writing d as d plus 2. So we'll get it as d plus 2 whole square minus 7 times d plus 2 plus 6. And we write this remaining 1 plus x here itself. So that's the particular integral after this. Now, if you can simplify this, see what happens. It is equals to, still I'll write this e power 2x as it is, and then 1 divided by, see if you can expand all this, d plus 2 whole square means d square plus 4d plus 4 minus 7 times d plus 2 ante 7d, then 7 times minus 7 times 2, it is minus 14 plus here is a 6. And of course, this 1 plus x we write as it is. And it is equals to e power 2x times 1 divided by, if you simplify this, first of all, I'm writing the square term, it is d square. Then we have 4d minus 7d. Look at it. 4d minus 7d is minus 3d. And if you add all the constants, it is 4 plus 6, 10. 10 minus 14, it's minus 4. And this you are operating on 1 plus x. Right? Understand, 1 plus 6 is a polynomial. When you have a polynomial on the right side, what we do, we have three cases which you should not forget. When it is an exponential function on the right side, see if it is like 1 by f of d into e power ax, we simply substitute d is equals to a. If it is like 1 by f of d into sine ax or cos ax, we simply substitute d square is equal to minus a square. But when if it is exponential, what you call polynomial function like this, x to the power of k, then see, we take lowest degree term common. Take out lowest degree term. So we should not forget this idea. And here the lowest degree term is minus 4, right? So keeping this e power 2x as it is, 1 divided by, I'm taking out minus 4 from these three terms. So it is 1 minus of, because it is a minus we brought out, so I'm taking a minus here, d square minus 3d divided by 4. And this you're operating on 1 plus x. Right? So then if I simplify this, it is equals to e power 2x into, here it is a minus 1 by 4. I'm writing that as it is. Minus 1 by 4 as it is. And now I'm taking this to the numerator. So what remains here, you see 1 minus of d square minus 3d by 4. All this to the power of minus 1. And if you operate this on 1 plus x, it is this. Now let's just simplify this. Look at the right hand side function. It is 1 plus x. Because it is 1 plus x, the highest degree in these two terms is 1. So if it is enough, if you take up to, I mean this expansion, when it is 1 minus x whole to the power of minus 1, we have it as 1 plus x square and so on, you know. In this expansion, it is enough if you take it up to x term, x power 1 term. Because here also the highest degree term is x power 1 only. So keeping that idea in mind, I'm just continuing this, you see, it is equals to minus e to the power of 2x by 4. I'm writing these two together into, if I expand this, it is 1 plus, see, I'm writing all this, d square minus 3d by 4. And see, I'm not taking the other terms because the on the right side, the highest degree term is x only. So all this you are going to operate on 1 plus x. Then it is equals to minus e to the power of 2x by 4. Now see, if you operate them, 1 operating on 1 plus x, it is 1 plus x. Plus here is a 1 by 4. I'm writing this aside. Then d square of 1 plus x. See, you have a 1 plus x, you know, if you differentiate it for the first time, differentiation of 1 plus x is, differentiation of 1 is 0, plus differentiation of x is 1. So even if you differentiate it for the second time, it's going to be 0, right? So using this idea, even all other higher order derivatives will also be zeros. D square of 1 plus x will be 0 minus 3 into differentiation of 1 plus x. You see, I've just verified it is 1. We'll get only this much. So this is equal to minus e power 2x by 4 into, we have a 1 plus x here. And here we'll see, we'll get it as minus 3 by 4. So that's a particular integral. Now, therefore, if you write the general solution is y is equals to yc plus yp. So that is y is equals to, see how much you got the complementary function, c1 e power x plus c2 e to the power of 6x. And here this one, minus e to the power of 2x by 4 into 1, you can also write it like this, you see, x, and see when it is 1 minus 3 by 4, we can write it as plus 1 by 4, you know, 1 minus 3 by 4 is 1 by 4, right? So it is x plus 1 by 4. This is your particular integral. I mean the solution, final solution. And see if anybody have any questions in that. If you have no other questions, let's take one more so that the problem becomes easy for us. I just want to take one question, which is, in fact, it was asked several times in the examination. So I just want to take that question. So with that question, we can conclude this. Right. Let me take a glass of water. Let's see, this is the question now. Solve d cube minus 7d square plus 14d minus 8 is equals to e power x into cos 2x. Right? Now let's just try to simplify this. So it's a clear, simple differential equation. And on the right side, we have a product of two different functions. So let us first of all find out the complementary function. So to find out the complementary function, we need to take what you call this auxiliary equation. So if you take the auxiliary equation, it is m cube minus 7m square plus 14m minus 8 is equals to 0, right? So randomly, even if you substitute m is equals to 1, you can see it satisfies the equation. So m is equals to 1 is one of the roots, but to find out the other two roots without wasting my time, I just want to use my calculator. So it is, see, I'm using this calculator here, as you can see on the screen. So I'm just clicking on this mode because equation is in the fifth option. I'm selecting equation 5. I mean the fifth option on the keyboard. And then you see, we are trying to solve a cubic equation. So it is in the fourth option. So I'm selecting number 4 here. So now I need to enter all the coefficients. So coefficient of m cube, you are given it as 1 in the question. Then I'm clicking on this is equal to button. Next, the coefficient of m square is minus 7. See, it is minus 7. Then again, I'm clicking on equality button. Then the coefficient of m, it is 14. Then the constant what you are given is minus 8. So if you just click on is equal to button again, so the first root what you have is 4. Then the next root you have is 2, x2 is 2. And the third root you have is 1. So 4, 2, 1 are the roots. Okay. So let's just proceed back. So this implies we can write m is equals to 4, m is equals to 2, and m is equals to 1. So this is using the calculator. Right. So now clearly the roots are clear, what you call real and distinct. So therefore, if you write the complementary function, it is yc is equals to corresponding to 4. It is c1 e power 4x plus c2 e to the power of 2x plus c3 e to the power of x. They are the roots. I mean, they are the complement, what you call, that's a complementary function. Now let's find out what you call the particular integral. To find the particular integral. So it is yp is equals to, see, I'm just sending it 1 divided by, I'm writing all that function as it is, d cube minus 7d square plus 14d minus 8. All this you're operating on, see, look at it, e power x into cos 2x. Right? Now, as we discussed already, before proceeding, let's just understand it this way. Because it is a function product of two different functions here, I need to send e power x to the left side, isn't it? When I send e power x to the left side, I need to replace this d in the denominator by d plus 1, isn't it? But you see, when you substitute d is equal to d plus 1, we need to take d plus 1 whole cube, then d plus 1 whole square, and then finally we need to all those things, isn't it? But to minimize my difficulty, let's understand it this way. To minimize the difficulty, look at this denominator. just before a few minutes ago, we got the roots of that expression. They are real and distinct. Because they are the roots, can't we write this denominator as d minus 1 into d minus 2 into d minus 4? We can factorize it like this, because they are the roots. We can factorize the denominator as this. And now, if you substitute d is equal to d plus 1, what happens to this? You see, d plus 1 minus 1, these two can be cancelled and we'll get a simple d. Right? So the problem can be simplified easily when you factorize this, because the roots are already known to you. Yes or no? So I'm just doing that to simplify these things. I'm writing it as d minus 1 into d minus 2 into d minus 4. Just to minimize my calculations, I'm doing this. No other idea. Even if you are not okay with this, you can simply substitute d is equal to d plus 1. You can expand it. I can, of course, simplify that. Now I'm writing this e power x on the left side to this 1 by f of d, and thereby I'm replacing d by d plus 1. So I have this d plus 1 minus 1, then d plus 1 minus 2, and here d plus 1 minus 4. So this into, there is no need to write e power x, but we need to write only cos 2x. Right? Now let's just simplify this. It is equals to, I'm writing this e power x as it is, and 1 divided by, after cancelling this 1, see, we'll get only 1, d here, and in the second term it is plus 1 minus 2, it is minus 1. So it is what you call d minus 1. Then in the next term, you see 1 minus 4, it is minus 3, d minus 3. And this cos 2x remains as it is. So this is equal to e power x into, see what I'm trying to do here. I'm just multiplying all these three. See, in the process, I'm just multiplying these two only. When it is d minus 1 into d minus 3, what you have here, you see, d into d square. We have d square. Then d into minus 3, minus 3d. Then minus 1 into d. Minus 3d minus d, it is minus 4d. And if you multiply the constants, minus 1 into minus 3, it is plus 3. You are now multiplying all this with d. There is one more d, So if you do all this multiplication, we'll get it as d cube minus 4d square plus 3d. First of all, I have multiplied these two, d minus 1 and d minus 3, which is d square minus 4d plus 3. And if I multiply all these three terms by a d, we'll get this. And you're operating all this on cos 2x. Right? Now, we know how to simplify this part. When you operate this on cos 2x, you know how to do that. What we do, if you recall, you need to now replace d square by minus d square, which is 2 square, 4, minus 4. So if you can do this, see what happens. This is equals to e power x into 1 divided by, as we discussed a few minutes ago, when it is d cube, we write it as d square into d, isn't it? So in place of d square, we write it as minus 4. So it becomes minus 4d, the first term. Then minus 4 into, in place of this d square, we write again minus 4. And this 3d, we write it as it is, 3d. All this operating on cos 2x. So this is equal to e power x into, if you can simplify this, it is 1 divided by, see, minus 4d plus 3d, it is minus d. And minus into minus plus 16 it is. Right? So this you're operating on cos 2x. Done. Now to get a d square here, you need to take rationalization, which so it is e power x into, in fact, you can understand this is like 16 minus d. So let me multiply and divide this by 16 plus d. That's quite simple to understand, So we have 16 minus d here, and you are multiplying it with 16 plus d. And of course, there is a cos 2x. So this is equal to e power x into, so we have a 16 plus d. I'm writing that as it is, but in the denominator, it's like a minus b into a plus b. So it's a square minus b square, So 16 into 16, it is 256 minus we have a d square. And you're operating this on cos 2x. Now, so because you have a function of d square, you need to again replace d square by minus 4, isn't it? So let me do that now in the next slide here. So it is e power x into, see what you have, 16 plus d in the numerator. And in the denominator, it is 256 minus d square was there. So in place of d square, now you're writing it as minus 4. And this you're operating on cos 2x. So this is equals to e power x into, see how much it is. When you add these two, it is 1 divided by 260. Look at it. See 260, and what remains? 16 plus d. This you are operating on cos 2x. So this is equal to e power x divided by 260. And if you operate these things, you see, it is 16 cos 2x plus differentiation of cos 2x, minus sin 2x into 2x differentiation, it is 2. So this is equal to, you can take a 2 common from these two things, you see. When you take 2 common from them, it becomes e power x divided by 130 into 8 cos 2x minus sin 2x. I just brought, 2 out of these two, so that I got, this is cancelled here. Now this is your particular integral, you see. Therefore, the general solution is y is equals to yc plus yp. So that is y is equals to, see how much is your complementary function, c1 421, so c1 e power 4x plus c2 e to the power of 2x plus c3 e to the power of x. This is your complementary function plus, the particular integral, you got it, this 1 e power x by 130 into 8 cos 2x minus sin 2x. So that is how you can calculate the solution of this differential equation. If anybody have any questions, you can raise your hand so that I'll unmute yourselves. Right, so with this, we have completed 2 more cases. The last one, what we have is x into v case that we discuss in the next class tomorrow. Right, so I'm just stopping this. Thanks for joining the class. See you tomorrow.